Problem 1, find the absolute extrema of the function f of x equals x squared plus 3x minus 4 on the interval -1 to 1. First step in finding the absolute extrema is to find the critical number. So we're going to take the derivative of the function, which will give us 2x plus 3. To find a critical number, we will set the derivative equal to 0. Subtract 3, I'll get 2x equals -3. And then from here, if I divide by 2, I'll get x equals -3/2. I do want to check -3/2, if you'll notice, is not in the interval. It's actually over to the left side. So we actually do not get to use that in our testing. So now what we're going to do is test f of -1 and test f of 1. When we test these, we go back into the original equation because we're looking for original y values. So if I plug -1 into that function, I will get -6. If I plug 1 into that function, I will get 0. So based on that, I know that my absolute max is equal to 0. The biggest y value is 0. And then my absolute min will equal -6. Problem number 2. Graph a function on the interval -2, 5 having the given characteristics. So the first thing that I'm going to do for this problem is, since my interval starts at -2, I'm going to make a dotted line at 2, -2. And since it ends at 5, I'm going to make a dotted line at 5, just so I know that where I'm headed in my interval. Okay, I like to deal with the absolutes first. Absolute maximum is at x equals 2. So when x equals 2, my graph is going to be the highest that it possibly can be. And I can really make that wherever I want, as long as my graph never goes higher than that. Okay, absolute minimum has to be at x equals 5. So I'm just going to go down here somewhere. So I just know my graph can never go any lower than that. Okay, I need to have a relative minimum at x equals -1. So over here somewhere, it's not going to be the minimum, but it's going to be close to it. So I'm just going to put something right there. So basically what needs to happen, although your graph can totally look different than this, I'm going to start anywhere that I want at -2, and I'm going to come down, and then I'm going to go back up, and then I'm going to come back down. That's not the only graph that you could have, but please notice that there is a relative minimum at x equals -1 because the derivative would go from negative to positive. It's not the lowest point, but it is a low point. And then I go up to an absolute max at x equals 2, and then down to my absolute min at x equals 5. Okay, problem 3. Does Rolle's theorem apply to the function f of x equals x squared minus x on the interval -1 to 1? I have 3 checks for this. The first thing that I want to do is to make sure that f is continuous. And if I'm checking for that, this is definitely a continuous graph. It's just a polynomial. Number 2, is f differentiable? To check for that, let's actually take the derivative. If I take the derivative, I'll get 2x minus 1. Is there anything of that the derivative can't equal? Nope, because there's no fraction, so it's definitely differentiable. And then my third check would be, does f of -1 equal f of 1? And so what I'm going to do is go back into the original function, or original, there we go. And when I plug in -1 for my x, I will end up getting 2. And when I plug 1 into my graph, I will end up getting 0. 2 does not equal 0, so no, Rolle's theorem does not apply. The way that I would explain it would be, no, Rolle's theorem does not apply because f of 1 does not equal f of -1. Problem 4. For the function f of x equals the square root of x minus 1, find the point guaranteed by the mean value theorem on the interval 1, 5. Okay, first of all, we usually go ahead and check, is that a continuous function? And if you would look, is it a continuous function or not? We know that x can't be anything, x has to always be greater than or equal to 1. And so notice everything that's between 1 and 5, I can plug those in. So we're good to go on that one. Step 2. If you took the derivative of that, I'm going to rewrite it as a 1/2 power first, and then I notice that that's a chain rule, so I'll get u to the 1/2. So my derivative will be 1/2 u to the -1/2 times the derivative of the inside, which would just be 1. So if I rewrite that, I will get 1 over 2 square root x minus 1. I just moved the u down to the bottom and made it to a square root. And then from here, I need to find out, can I always take the derivative? No, I can't take the derivative, and I actually can't take the derivative at 1, but the mean value theorem actually says that it just has to be differentiable on the open interval 1, 5, so it is okay. 1 is not included in this open interval, so it's okay. It is differentiable. Okay, since it is, we have a few steps. The first one is we actually want to find the slope. So if I find the slope, I know my x values are 1 and 5. When we're finding the slope, we're going to go into the original problem to get our y values. So if I plug 1 into the original problem, I will get 0. If I plug 5 into the original problem, I will get 2. So the slope is going to be 2 minus 0 over 5 minus 1, which gives me 2 over 4, which gives me 1/2. Okay, second thing is we want to find the derivative, which we already did. And then my third step is to set the mean value theorem states that somewhere the derivative equals the slope. So we'll set the derivative equal to slope. And I've taught you that if you do have two fractions that equal to each other, to cross multiply. So I will have 2 square root of x minus 1 equals 2. I'll then divide both sides by 2. So I'll get square root x minus 1 equals 1. From here I'll square both sides. So I'll get x minus 1 equals 1. And then if I add 1 to both sides, I will get x equals 2. And that is in the interval, so that is the point guaranteed by the mean value theorem. Okay, problem number 5. This one says a farmer has 20,000 feet squared area for a rectangular pen. The barn wall will be used as one side of the pen. What dimension should be used so that the amount of fencing is a minimum? How much fencing will be used? One thing that I'm going to do is go ahead and label this. We'll label this as x and these two sides as y. The biggest thing here, we want the fencing, the amount of fencing to be a minimum. Well, how much fencing is, I'm just going to put f equals, how much fencing would I need? I'd need 1x and I need 2 y's. Okay, my side trip is going to deal with this 20,000 feet squared. I notice that this says feet squared, which has to do with area. Okay, the area of this rectangular pen, since it's a rectangle, is just length times width. So it will be x times y. They did tell me that the area was 20,000. Okay, I can solve for either x or y. It looks like it would be most convenient to solve for x. So I'll divide y. So I'll get 20,000 over y is equal to x. I now will substitute that up into my fencing equation. So I'll have 20,000 over y plus 2y. Okay, from here we're going to take the derivative, but I'm going to rewrite this as 20,000 y to the negative 1 plus 2y first. Now if I take the derivative, I'll get negative 20,000 y to the negative 2 plus 2. I'm going to simplify that one more step. I'm going to bring my y down to the bottom, so I'll get negative 20,000 over y squared plus 2. And now I'm going to set it equal to 0 because we want to find a critical number. Okay, I am going to, at this step, get a common denominator, which would be y squared. So I now will have negative 20,000 plus 2y squared over y squared equals 0. And if I would like to do that, I would like to determine where the numerator is going to equal 0. So I'll get negative 20,000 plus 2y squared equals 0. I'm going to add 20,000 to both sides, so I'll get 2y squared equals 20,000. I'll now divide by 2. So I'll get y squared equals 10,000. And then I will square root, and if I do that, I get y equals 100. If I set the denominator equal to 0, I'd get y squared equals 0 or y equals 0, and it would make no sense to have a fence that didn't have a width. So that we can just cross it off. Okay, to get the x value, I'm going to go right back up into this equation right here. So x will equal 20,000 divided by 100. And when I do that, that will give me that x is equal to 200. So it says what dimensions should be used. I would say x would equal 200 feet and y would equal 100 feet, and then it said how much fencing will be used. So I'm going to go back up into my fencing formula. So I'm going to have fencing equals x, which is 200, plus 2 times 100, and that will give me 400 feet of fencing.